Hi, welcome to Apex Math. Today we are going to look at how to solve exponential word problems, and especially how to know what type of equation should I use when I'm solving these, how to figure out what it is that I need to write down in order to get the correct answer for different types of word problems. So let's go ahead and get started. And the first type of problem that I'm going to do is we're going to look at a car, and I'm not going to write out the whole word problem, just the main ideas here. A car, we're going to say, costs $10,000. And that because most cars, the price will depreciate over time, and this particular car, it depreciates or decreases at a rate of 7% per year. So the question becomes, what will the cost be after 10 years? What will be the value of the car after 10 years? And what type of equation should we use to solve it, and also talk about some of the meaning behind the equation type that we need. Well, we could figure this out going 1 year at a time. We could say, well, in the first year, and this is always a good way to go if you're completely lost and you don't know what to do, you can just kind of work it out through brute force. So you can say, well, in the first year, it's $10,000, but it loses 7%, so I'd multiply 7% times 10,000. I'd find the value that it has lost after 1 year, and I'd get that new value, and then I'd continue that process for a total of 10 years. So that's sort of working it out with brute force, but not so much using the math and the idea of the concept of building an exponential equation, which is sort of the goal of Common Core or algebra or whatever course that you're in, that we're trying to do when we present these problems, is we'd like you to come up with an equation, because that's how the real world actually works, is that we have these equations, this math, to model real world situations. And anyone who goes into a field that uses mathematics, that's what they do, is they take these real world situations, model it with a math equation, and then they can calculate out values not just at the 10-year mark, but at the 100-year mark, or at any particular year they would like. So when we are solving this type of equation, this is sort of a value type equation where we're dealing with appreciation, which is where the value goes up, or the depreciation where the value goes down. So if you buy a house, most of the time, over time, if you buy a house, the value will appreciate because of inflation and things like that, and the value of the house increases over a period of time. However, cars don't do that. Cars, we don't own them long enough, and they are mechanical, they fall apart, so they depreciate. So when we try to figure out this type of equation, we want to use the formula for appreciation and depreciation problems of y equals the, and this letter can be any letter you want. I'm going to just call it P for right now, because it's usually used in a lot of calculating interest type problems. But the principal, or the initial amount that the car cost or the house cost, but that starting value. So that's what P is going to stand for, is our starting value. And then I have a choice here. I can either have things appreciate, which means they go up in value, or depreciate and they go down in value. And they're going to go up or down at a particular rate. So if I appreciate in value, then I'm going to add 1 to the rate. But if it depreciates in value, I'm going to do 1 minus the rate. And that's what goes into this set of parentheses here. And then it is always raised to the power of x, where x is the number of years. Or sometimes it can be the number of periods in a interest type problem. But generally, for speaking for now, we're just going to say the number of years. So in this case, because we are looking at the depreciation, we want 1 minus the interest rate. So we're going to put in here 1 minus r. So that becomes the formula that we use. So anytime you have something that you're investing or a piece of property that's going up or down, this is the general formula that you're going to use, is y equals the initial value, p, and this is going to be either 1 minus or 1 plus, depending on whether you're appreciating or depreciating, and then raised to the x power. And it's because we're raised to the x power that our variable is up in this exponent position. This is why this is called an exponential equation. Exponential equations are equations where the variable x is up in the exponent position. So for this particular case here, we have, very simply, it becomes a very simple problem. And I'm not going to, because we're doing so many different types of problems here and we want to focus on how to set them up, I'm not actually going to calculate the answers for all of these. You can just punch that into your calculator. I'm just going to talk about how we figure out which type of equation we need to use and how to set it up. So in this case, we would have y equals the initial value of the car, $10,000. It's depreciating, so we're going to do 1 minus. And the rate is 7%. And we always write interest rates as a decimal. We never write it as the 7%, because 7% is actually not a number in and of itself. Percent means divide by 100. So this means 7 over 100, which it's easier to just write, instead of as a fraction, to write it as a decimal. So we're going to have 1 minus 0.07 to the x, where x is the number of years that we are interested in finding out the answer for. So for this particular case, we would have y equals 10,000 times 1 minus 0.07. So we do that because it's in parentheses, and we know our order of operations says we always do parentheses first. Remember, please excuse my dear Aunt Sally. So we have 0.93 is what 1 minus 0.07 is equal to, and it's raised to the x. In this case, x is going to be 10 because we want to find out its value after 10 years. So our final equation that you would punch into your calculator is 10,000 times 0.93 caret, that means raised to the power of 10. So if you type that into your calculator, you'll get the actual numerical answer. Now, one thing to note here is when you look at what's in parentheses here, sometimes you will find that they will give it to you already in the condensed form. This we can think of as sort of the expanded form, and this is the condensed form. If it's in the condensed form, if this number is less than 1, then we know it was a depreciation problem, because it had to have been 1 minus some number to get that number less than 1. If it was an appreciation problem, then we will see something where that value there is a number greater than 1. Say y equals, let's say we had a house for 100,000 and it appreciates at 3% per year, so it would be 1 plus 0.03, so its condensed version would be 1.03 raised to the x. So you can see here, if this number is greater than 1, then that means we have a situation where it is exponential growth, and this one is exponential decay. So that's other terms we use for appreciation being exponential growth and depreciation being exponential decay. All right, so let's look at a different type. Let's say we're looking at the daily cost of a patient in a hospital, the daily cost of a patient at a hospital in the United States, and it has increased at about 8% a year since 1985. 8% per year since 1985. So if back in 1985, the value or the cost for a patient per day is $460, then what would the same cost for the patient per day be in the year 2000? Well, so again, we see that we have an initial value, 460, and the value is increasing, so it's exponential growth. So we're going to use the initial value, y equals the initial value, 1 plus that rate of 0.08, and again, we're going to raise it to the x, the number of years. And in this case, we'll say the number of years was 15 years between the year 2000 and the year 1985. So on the calculator, again, you would do 460 times 1.08 caret 15, and that would give you your answer to this problem. All right, so let's look at the case of half-life. Half-life is often problems that are given. And let's say we have something called cesium, and I am not a science person, so excuse me if I'm saying that wrong, 137, and it has a half-life of 30 years. A half-life means the amount that you have, the initial amount, decreases or is cut in half every time period. So every 30 years, the amount of cesium that we have is going to decrease by 50% or go down by half. So let's say that we have 30 grams of it to start, 30 milligrams, and we want to know after 60 years how much are we going to have left if it cuts in half. So if we look here and look at the time it takes to cut in half versus the time we have, how many times will it be cut in half? Well, it'll be cut in half once at the 30-year mark, and it'll be cut in half again at the 60-year mark. So it will be cut in half twice. So essentially our time frame is 2 periods of being cut in half. So when doing half-life, I like to look at it by how many periods, and that is the value that x takes on, is the number of periods. It does not take on 30. It does not take on the value 60. It takes on the ratio between these two values. If you take 60 and divide it by 30, you will get that value 2. So how do we set up the equation? Well, half-life falls under this same formula, but it already has it's already in the condensed version form. A here is that initial amount. B is the rate at which we're changing. And the rate we're changing here, if we're cutting something in half, is we are essentially doing 1 minus 0.5. We're decreasing by 50%. Or we can just look at it as a half-life of being 0.5, which equals 50%. So our B in half-life problems is always going to be 0.5, which is the same as being cut down at a rate of 50%. So if I take my initial value, which is 30 milligrams, 30, and then I multiply it times the rate at which I'm decreasing, 50%, and I raise it to the x. But again, with half-life, that's the only tricky part, is x is not, as I mentioned, either of the numbers in the problem. X is the number of periods that happen which is found by the ratio of those two numbers. Sometimes teachers like to write it like this: 30 equals 0.5x over 30, and then you can plug in 60 for x. 60 over 30 gives you 2. So it will depend on which way your teacher likes you to write it. I prefer personally just to use x and know that x has to be the number of periods because it's the same for all problems. Or you can put the ratio in here of what you need to do so that when you plug the other value into the equation, you get the number of periods. So essentially, on our calculator, what would we have to type in to get the answer? Well, we would type in 30 times 0.5 caret 2. Again, because there are 2 periods where it is cut in half. It is cut in half 2 times. Cut in half 2 times, and that's where that number 2 comes from. This is always 0.5 if it's a half-life problem, and this is the initial amount. So all of these equations end up being this form y equals ab to the x. The other ones we did, that b was just not in condensed form. We looked at it as the 1 plus r or the 1 minus r. All right, so let's do one more half-life problem. Let's say we have this, and it has a half-life of 6 hours, 6-hour half-life. And let's say we have 80 milligrams of it. And we want to know how much we have left after 24 hours. How much left after 24 hours? So again, I need to find the number of periods, which is going to be the ratio between these two numbers. So if I say in 24 hours, how many 6-hour periods are there? I do 24 divided by 6, and I get 4. So there's 4 periods. So my x that I like to use is going to be equal to 4. After that, setting it up is pretty easy. The initial amount, it's a half-life, so it's going to be a 0.5, and we're going to raise it to the 4 because there's 4 periods. So on a calculator, it would just be 80 times 0.5 caret 4. All right, let's move on to the next type. Now let's say this time that we have 10 CDs and that we like to buy CDs and that we double the number of CDs that we buy every year. So how many CDs will we have after 5 years? So this is not a half-life problem, but we are still increasing at this doubling rate. So we're going to still use, as we use with everything, y equals ab to the x. And we know that the a is the initial amount. So we know that 10 goes here. So what is the value that we need to put in here for b? Well, b is the rate at which things are changing. When it was half, we put in half. If we're doubling, then we're multiplying times 2. It's increasing at a level of doubling every year. So if it's doubling, we use 2. If it's tripling, we use 3. Quadrupling, we use 4. So this value depends on the rate. So b simply becomes 2 in this problem. And then x is the number of periods that it's going to happen. Well, if it's every year, and we want to know 5 years, that ratio is simply as it would be, just x is equal to 5. It's the total number of years. So y equals 10 times 2 to the 5th, or on the calculator, 10 times 2 caret 5. right? So let's say that we have, in biology, we have a process called mitosis, and that's a process of cell reproduction in which one cell divides into two identical cells. So one cell divides into two cells. So let's look at E. coli, and that's a fast-growing bacteria that you do not want to have in your system, but it can reproduce itself every 15 minutes. Reproduces, there we go, every 15 minutes. And if we start off with 100, whatever it's measured in, 100 E. coli, then how much E. coli will we have after 1 hour? So again, we want to use y equals ab to the x, our standard formula, and we're just applying it to different situations here. The initial amount is 100, so we have 100, and then we have to look at what happens to the E. coli. Well, one cell divides into two cells, so it is essentially doubling. So we're going to say a 2, again, when we see a double, and we're going to raise it to the x. But again, x is the number of periods that it happens. So if we have 1 hour and every 15 minutes, we need to know, well, first of all, notice that this is in minutes and this is in hours. So 1 hour is the same as 60 minutes. Now that they're in the same units, I can go ahead and divide, take the ratio in order to find my x. So x is equal to 60 divided by 15. How many 15 minutes sections are there in 60 minutes? Well, that is equal to 4. So if I plug in 4 here on my calculator, I'd have 100 times 2 caret 4. All right, let's say we have a balloon, and it has, at the end of each day, 3/4 the amount of air, or we'll say helium maybe, 3/4 as much helium as the previous day. So if we start off with 5,000 cubic centimeters of helium, how much helium will we have after 9 days? Well, you can probably figure out the process. We're going to use y equals ab to the x. A is the initial amount, so 5,000. B is what is happening to our helium. Well, it's reducing at a rate of 3/4 each day. So we're reducing by 3/4 each day, and how much do we have at the end of 9 days? So that becomes x, and we now have x, since we just have the ratio of 1 day to 9 days, x is equal to 9. So we end up with 5,000 times parentheses 3/4, because it's a fraction if you're entering it into your calculator, caret 9. Now what if we have something that triples? Suppose we have 20 rabbits, and the rabbit population triples every half year. So the population triples every half year. Then how many rabbits will there be after 2 years? So y equals ab to the x. A is the initial number of rabbits. What's happening to the rate of the rabbits? They are tripling. So it is changing at a rate of 3 to the x. Trickiest part of this is figuring out that value of x. So here we're in years. Here we're also in years. So this is 1/2 a year, and this is 2 years. So I can say 2 divided by 1/2, which is equal to 4. So there are 4 1/2 years in 2 years, which you could probably have figured out in your head. So x is going to be 4. So on my calculator, I'm going to have 20 times 3 caret 4. So all of our problems we dealt with were of the form y equals ab to the x. A was equal to the initial amount, and b was our rate of change. And x is the number of changes that happened, which we called periods, which often we have to divide the ratio to find. Now, sometimes when dealing with appreciation and depreciation, b may not be in condensed form yet. So if it's appreciation or exponential growth, then we do b is equal to 1 plus r. Or for depreciation or decay, then b is equal to 1 minus r. So sometimes we have that extra step where we have to find that value of b ourselves by adding 1 to it or 1 minus. And we talked about the different situations where that occurs. The final example, let's just talk about a regular investment example. So let's say that you are saving for college and you have $10,000 that you put into the bank and you're going to save for 5 years. And that the CD that you chose is a 6% CD. So it increases 6% per year. So how much money will you have at the end of 6%? Well, we know that this is an increase, right? Because we're saving and we're gaining interest. So it's an appreciation problem. But it's not where we have a number like where it's doubled or half or 3/4 of the rate. In this case, we're just given the percent at which we're appreciating. So we're going to have to use that 10,000 times its appreciation. So we're going to do plus 1 plus 0.06 to the 5 years. Now, you may do something that deals with compounded interest. That's where you start getting interest upon interest. And we'll do that in another video, but just a little preview. Let's say that instead of every year, at the end of the year, you collect your interest. But at the end of every month, they give you their interest. So if they do that, then you start building interest on interest. So how do we adapt this formula for compounded interest? So that's what I just want to talk about briefly, is adapting for compounded interest. So what we're doing is we're saying, instead of looking at it on a yearly basis, let's look at it on a monthly basis if we compound monthly. So it's 6% a year, but what percent would that be per month? Well, to find out, I would have to divide 6% by 12. But then how many times would I collect that interest? Well, the number of periods would be not 5 anymore. It would be 5 times 12, because I'm getting my money is being recalculated for interest at every period. So there's 60 periods now because it's done monthly rather than yearly. So when you adapt it for compounded interest, the only change you have to make, and a lot of times teachers make you memorize this whole new formula, you don't need to do that. It's your same formula that you've been working for. The only thing that's different is that you divide here by the rate at which you're compounding. If it's monthly, you would divide by 12. If it's quarterly, you divide by 4. If it's yearly, you divide by 365. And then whatever you do here, you have to multiply up here by that same value, because you have to change the periods to match the fact that you've now broken your interest rate down to per day. So you have to then look at the number of periods, which is the number of days in that period rather than the number of years. So the formula does not change at all, with the exception of those two little things here, is dividing here and multiplying by that same number. And that number there is often called n, where it's called the compounding rate. So it would be A times 1 plus your rate divided by n, and then t times n. So again, same formula. The only thing that's different is we've divided to make our rate monthly, yearly, or well, it already was yearly, monthly, quarterly, daily, and then we made our number of periods match that as well. So that is your compound interest formula. So important to know, y equals ab to the x is really the only formula you need to know. You just need to know those two modifications for certain situations for what you need to do in the case of compounded interest and exponential growth and decay with appreciation and depreciation. I hope this video did a good job of explaining how to work with word problems that are the type for exponential growth. Again, this is Apex Math, and we appreciate it if you would like our videos for us, and any comments that you have or suggestions of future videos that might help you with your math homework, we'd be happy to hear them. And have a great night.